Alright, ladies and gentlemen, this is going to be another video on Lussac's Law. We're going to be going into detail on how to do some more problems. So remember the formula, P1 over T1 is equal to P2 over T2. Remember, P1 is going to stand for our initial pressure, T1 is going to stand for our initial temperature, P2 stands for our final pressure, and then T2 is going to stand for our final temperature. Alright, so let's go through and calculate the final pressure in atmospheres for a gas with an initial pressure of 1.2 atmospheres. We have 78 degrees Celsius, and it's going to be cooled to negative 32 degrees Celsius. So first off, our formula here is going to be P1 for T1 is equal to P2 over T2. Now we are working in Celsius here. To get to Kelvin, Kelvin is equal to our Celsius plus 273.15. We can just add 273 to get that. So if we go through and do this, well, we need to convert 78 degrees Celsius or 78 degrees Celsius into Kelvin. So we're going to do 273. We are going to add that to, it looks like 78 degrees Celsius, so plus 78. We'll get a final answer of 351 degrees Kelvin. Then down here, negative 32 degrees Celsius, we're going to do 273 plus negative 32. So negative 32 or minus 32, we're going to get a final value of 241 degrees Kelvin here. So here are our Kelvin temperatures. Now we can go through and do the calculation. So we're going to put in 1.20 ATM. We're going to put this over. Our initial temperature is 351. Let's do 351 degrees Kelvin. Set that equal to, and then we'll go through and do this one. P2 is what we're solving for, 241 degrees Kelvin. So if we do the math here, we multiply both sides by 241 degrees Kelvin. This will cancel, multiply by 241 degrees Kelvin. Kelvins cancel, I'm left with just atmospheres. So we'll do 1.2 divided by 351, and then we will multiply that by 241. We'll get a final answer of a P2 value of 0.82 atmospheres. Does this make sense? We cooled it. If our temperature went down, our pressure also had to go down as well. Alright, so let's go through and look at our next one. A tank of argon gas with a pressure of 0.950 atmospheres at negative 32 degrees Celsius is heated to 28 degrees Celsius. Again, we're trying to calculate final pressure. P1 over T1 is equal to P2 over T2. If we go through and do this calculation here, well, remember we're going to convert this into Kelvin. Kelvin is equal to Celsius plus 273. You guys don't have to worry about the 0.15. So 273 plus negative 32. That's going to give us a negative 32 degrees Celsius is equal to 241 degrees Kelvin. Now if we do this for 28 degrees Celsius, well, let's go through and do this one. So we're going to do 273 plus 28. So 28 degrees Celsius is equal to 301 degrees Kelvin. Okay, perfect. So now we can go through and punch this into our formula here. Initial pressure is 0.950 atmospheres. Divide that by our temperature. Initial temperature was negative 32. We're going through and heating it to 28 degrees Fahrenheit, so 241 degree Kelvin. Then we'll set that equal to, we are solving for P2. And we'll go through with our temperature here, 301 degree Kelvin. Multiply both sides by 301 degree Kelvin. This will cancel out. Multiply by 301 degree Kelvin. So we'll do 0.950. We will divide that by 241. And then we will multiply that by 301. When we go through and do this, well, we get 1.18. Looks like 86 atmospheres. Now our temperature went up, so does this make sense? Our pressure went up. Remember, they are directly proportional. So in this case, yes, this makes sense. So we have a gas with an unknown pressure with a temperature of 46 degrees Celsius. Same gas has a pressure of 2.35 atmospheres when the temperatures drop to negative 15 degrees Celsius. We're trying to figure out what the initial pressure is in this problem. P1 over T1 is equal to P2 over T2. Now we're solving for P1 this time. So we're going to have to go through, again, convert into Kelvin, and then we're just going to have to solve for this variable instead of this one. All right, so 46 degrees Celsius. To get this to Kelvin, remember Kelvin is equal to whatever it is in Celsius plus 273.15, and we're just going to use 273. So we're going to do 46 degrees Celsius plus 273. We're going to set that equal, so 46 plus 273 is going to be equal to 319 degrees Kelvin. So you can see that 9. And then what we'll go through, we'll do negative 15 degrees Celsius plus our 273. So negative 15 plus 273. We'll get a final value of 258 degrees Kelvin. So we initially had a temperature and we're cooling that temperature. So temperature is going down, so therefore our pressure must also be going down. So if we go through and look at this one, well, let's punch it into our formula. So our initial temperature is 319 degrees Kelvin. We're solving for P1, so that's what we're solving for. We'll set it equal to 258 degrees Kelvin. Then our final pressure is 2.35 atmospheres. Pressure should go down. We'll multiply both sides by 319 degrees Kelvin. So this will cancel. Multiply by 319 degrees Kelvin. So 2.35 divided by 258 is going to be equal to that times 319. Pressure went down. So we got a pressure value, P2 value, equal to 2.90 atmospheres. And let me just make sure I go through and correct this. When I was saying the pressure should go down, our pressure here should be lower than our pressure here, because we went through and we went from 46 to 15 degrees Celsius. It's probably not the best explanation. Technically, if we're thinking about this, right, if we go from 15 to 46, our pressure should go up to 2.9 atmospheres. So if we look at this one, a gas sample has a pressure of 766 millimeters of mercury. And we don't have the temperature for this initial temperature. So if we're looking at P1 over T1, P2 over T2, well, we are solving for T1 here. So if we're going through and doing this, let's go through and plug this in. P1 is 766 millimeters of mercury. Solving for T1, I have 744 millimeters of mercury. Dividing that by 22 degrees Celsius plus 273 is equal to 295 degrees Kelvin. 295 degrees Kelvin. So now all I have to do is solve for T1. So I'll do 744 divided by 295, and that should be 2.52. Multiply I'll go through and multiply both sides by T1. Multiply by T1, and then divide by 2.52 on both sides. 766 divided by 2.52. Well, I'm going to get an initial temperature of 303.96 degrees Kelvin. Convert this back to Celsius. We'll go through and subtract 273 minus 273 here. We'll get a Celsius value of 30 degrees Celsius here.